A single protein folding experiment can generate more data in one day than all the protein research done in the 1970s combined. And an AI can now sort through that avalanche in seconds instead of years. For most of the history of science, the bottleneck wasn't our imagination. It was time. It took months to run an experiment, more months to analyze it, and years to compare it to everything else that had ever been done. Today, the bottleneck is different. We are drowning in measurements, petabytes of telescope images, genome sequences, climate records, particle collisions. The new challenge is not, can we measure it, but can we understand what we've already measured? And that is where artificial intelligence is quietly rewiring how discovery works. When scientists talk about AI in research, they're not talking about sentient robots in lab coats. They mostly mean a family of tools called machine learning models, algorithms that learn patterns from examples instead of following a fixed recipe written by a human. You show them millions of labeled galaxy images, and they learn to recognize galaxies. You feed them spectral fingerprints of molecules, and they learn to predict chemical properties. At their core, these systems are function approximators. Given an input, estimate the most likely output based on everything they've seen so far. That sounds simple, almost disappointingly so. But scale it up to billions of data points, and tiny improvements in pattern recognition suddenly become engines of new physics, new biology, and new views of the universe. Let's start with speed, because it's the most obvious and the easiest to underestimate. In 2007, the Galaxy Zoo project invited volunteers to classify about 1 million images from the Sloan Digital Sky Survey, deciding for each one whether it was a spiral, an elliptical, or something stranger. It was a triumph of citizen science, but it still took around 2 years of human attention. Today, a deep convolutional neural network can be trained on that human-labeled dataset and then classify new galaxies at a rate of tens of thousands per second, with accuracy that rivals expert astronomers. The key shift is subtle but profound. Humans move from doing the task, one galaxy at a time, to supervising the task, defining what counts as a good classification, checking edge cases, and deciding what to do when the AI flags something weird. That change in role is crucial. AI speed doesn't just make the same science faster. It makes different science possible. When a model can skim through an entire sky survey and highlight the 1 in a million anomalies, gravitational lenses, bending light into arcs, supernovae flaring and fading over days, scientists can shift their curiosity toward the rare, the transient, and the unexpected. It's like moving from reading every page of a library manually to having a tireless assistant that can instantly say, here are the 5 books that break all the usual rules. Maybe start with these. Speed alone would just mean we get wrong answers faster if we're not careful. What makes AI matter for discovery is when it also improves accuracy and reliability. Large experiments are full of noise, random fluctuations, detector glitches, cosmic rays hitting sensors, human errors in recording. Traditional analysis methods, like fitting a line to data with least squares, make assumptions, for example, that the errors are nicely distributed around the true value, like a bell curve. Machine learning models, especially probabilistic ones, can learn more realistic error structures. They can say not just the answer is 3.7, but the answer is probably between 3.5 and 3.9. And here's why we're uncertain. A striking example comes from gravitational wave astronomy. Experiments like LIGO and Virgo measure changes in distance smaller than 1,000th of a proton's diameter over kilometers-long arms, caused by black holes and neutron stars merging hundreds of millions of light-years away. The raw output looks like static from a badly tuned radio. Physicists used to rely primarily on matched filtering. You compare the noisy data against a huge library of theoretical waveforms, predictions from general relativity for different masses and spins, and look for a match. This is computationally expensive and limited by the templates you thought to include. Neural networks, once trained on simulated mergers, can scan incoming data streams in near real time, recognizing the subtle chirps of a merger weeks faster than traditional pipelines, and they can sometimes maintain sensitivity even when the noise behaves in unexpected ways. They don't replace the underlying theory, but they act as incredibly sharp ears, listening for patterns that would otherwise be lost. On our own planet, AI is transforming how we see dynamic, messy systems like weather and climate. Traditional numerical weather prediction solves the fluid dynamics equations of the atmosphere on a grid, advancing them forward in time, essentially simulating every swirl of air. This is accurate but incredibly expensive. In 2022, an AI system called GraphCast, developed by Google DeepMind and partners, showed that a machine learning model could predict global weather up to 10 days ahead more accurately than the gold standard European Center for Medium-Range Weather Forecasts, while running thousands of times faster. Instead of explicitly simulating the physics, GraphCast learned, from decades of reanalysis data, how patterns in temperature, pressure, humidity, and wind tend to evolve. Importantly, its biggest advantages show up in extreme events. The early formation of hurricanes, rapid intensification, or sudden stratospheric warmings that can disrupt jet streams. That matters for science, not just for forecasting flights, because better, faster predictions let researchers run more what-if experiments and study rare atmospheric dynamics in much greater detail. Now let's go beyond speed and accuracy and talk about something deeper. AI as a hypothesis generator. Traditionally, theory came first. Observation tested it. You write down Maxwell's equations, then you build radio antennas. You propose general relativity, then you measure starlight bending during an eclipse. Today, in some domains, the order is starting to blur. You collect massive observational datasets, you let AI roam through them, and the model comes back with patterns you didn't know to look for, regularities that then beg for a theoretical explanation. Exoplanet astronomy is a perfect example. Space telescopes like Kepler and TESS watch the brightness of hundreds of thousands of stars for years, looking for the tiny periodic dimming caused when a planet transits in front of its star. The signal can be as small as a 1 part in 10,000 drop in light, buried in instrumental noise and stellar variability. Early on, scientists handcrafted rules. If you see a dip that's roughly this deep, this long, and repeats with this regularity, flag it. Machine learning models, particularly convolutional neural networks, don't need such rigid rules. Trained directly on light curves labeled by humans, they learn the complex multidimensional shape of a convincing transit. And they've already helped confirm planets that would have been dismissed as noise or false positives by traditional pipelines. Even more interestingly, AI is starting to spot stars whose variability doesn't fit known categories at all, hinting at new classes of stellar behavior or planetary systems that defy our current architectures. If space feels too abstract, consider something that might one day be in your bloodstream: new drugs. The number of possible small organic molecules that obey basic chemistry rules is estimated to be around 10 pounds 60. That's a 1 followed by 60 zeros. For comparison, there are about 10 pounds 22 stars in the observable universe. No human, no classical supercomputer can brute force explore that chemical universe. AI models, especially generative ones, act like guided explorers. They learn the statistical structure of known molecules and their properties, then propose new candidates that are likely to have desired traits, for example, binding strongly to a viral protein, or dissolving well in water but not breaking down too quickly in the body. Systems like DeepMind's AlphaFold don't design drugs directly, but by predicting the 3D structures of proteins from their amino acid sequences with near-experimental accuracy, they provide a detailed map of the molecular machines inside cells. That map drastically narrows the search space, because you can now ask, given this specific fold, this exact binding pocket, what molecules might fit here, like a key in a lock? What's new isn't just that this is fast, although going from years of crystallography experiments to minutes of AI inference is a seismic change. It's that AI systems are learning the implicit rules of biophysics by example. They're distilling patterns that evolution discovered over billions of years, and then they're letting us play with those patterns, not blindly, but with increasing precision. We can systematically explore what-if questions that would be biologically impossible or ethically unacceptable to try directly in organisms, at least as first passes in silico, before moving to the lab. Even in domains where experiments are rare and expensive, like particle and neutrino physics, AI is becoming essential. Detectors at the Large Hadron Collider create up to 1 billion proton-proton collisions per second. Only a tiny fraction can be stored. Trigger systems, increasingly aided by AI, decide in microseconds which events look interesting enough to keep, maybe a rare decay or hints of a new particle. Later, offline, more sophisticated neural networks reconstruct what actually happened, which tracks came from which particles, where vertices indicate short-lived states, whether a given jet of particles is more likely from a top quark or from background noise. In giant neutrino observatories, AI-based reconstruction can tease faint Cherenkov light patterns from the darkness and infer the direction and energy of ghost-like neutrinos that pass through light-years of lead-equivalent shielding without interacting. In both cases, these are not just convenience tools. They change the sensitivity frontier. They let us ask questions about the fundamental forces in particles with finer resolution and in regimes that were previously out of reach. AI's role isn't limited to exotic frontiers. It's also revealing hidden systems here on Earth, quietly running beneath our feet and over our heads. Satellite constellations now monitor the entire planet daily at resolutions down to a few meters. Raw pixels show forests, fields, oceans, cities. AI turns those pixels into dynamic maps of biomass, soil moisture, glacier movement, and even underground water depletion inferred from subtle surface changes. For example, by analyzing tiny variations in gravity measured by satellites like GRACE, combined with climate and land use data, machine learning helps estimate how fast aquifers are being drained in regions where there are no monitoring wells. In agriculture, models trained on multispectral images and ground truth yield data can predict crop stress weeks before it's visible to the naked eye, allowing targeted irrigation or fertilizer use. For ecologists, this means you can move from isolated field sites to near global experiments. How do plant communities respond to droughts of a given intensity? How do insect populations track changes in nighttime light pollution? AI is the connective tissue that links scattered measurements into coherent, testable stories. Of course, any tool this powerful comes with serious caveats. AI models are only as good as their training data and the assumptions built into their architectures. If the data is biased, skewed towards certain kinds of galaxies, or human populations, or weather regimes, the predictions will be biased too, often in subtle ways. Overfitting, where a model essentially memorizes its examples rather than learning general principles, is a constant risk. That's why the most careful scientific uses of AI lean heavily on interpretability and cross-checking. Researchers probe what features a model is using, test it on synthetic data with known ground truth, and compare its results to those from independent methods. They ask, does this pattern hold up when we change the instrument? The algorithm? The calibration? In that sense, AI is not replacing the scientific method. It's giving us new, more sensitive instruments inside the method. Microscopes for data. The biggest story is that AI is shifting the geometry of discovery itself. For centuries, scientific progress was limited by what a single mind or a small group could calculate and compare. Then computers extended that to what we could program explicitly. Now, with machine learning, we're stepping into a regime where we can ask systems to find patterns we didn't know to encode, across data volumes we could never manually inspect. That doesn't make human curiosity obsolete. If anything, it makes it more precious, because we need to decide which of the AI's countless possible questions are worth chasing. Which strange galaxy, which suspicious dip in a light curve, which anomalous particle event hints at new physics instead of new bugs. As we build these systems into telescopes, microscopes, particle detectors, and climate models, we are effectively giving our instruments something like a nervous system, a way to notice, to prioritize, to surprise us. The real frontier is no longer just about looking deeper or farther, but about seeing differently. And that raises a deeper question. If AI can find patterns we didn't anticipate, what happens when it begins to point toward phenomena that don't fit any of our current theories at all?